Dear students, in the last class we have seen different types of semiconductors, intrinsic semiconductor and extrinsic semiconductors. Extrinsic semiconductors are formed using the process of doping. Doping is nothing but the process of adding the impurities to the semiconductor. If you add third group elements to a semiconductor, there will be a formation of p-type semiconductor, and if you add fifth group elements to a semiconductor, you can form the n-type semiconductors. Now in this class we are going to see the charge densities in a semiconductor. But before going for this concept, let me tell the definition of this mass action law, which is the most important law in semiconductors. So what is mass action law? Mass action law is nothing but the product of free electron and hole concentration must be equal to the square of the intrinsic concentration. And you know, the electron concentration and hole concentrations are measured per meter cube. That means N is nothing but electrons per meter cube and P is nothing but the holes per meter cube. So, the product of the free electron and hole concentrations must be equal to the square of the intrinsic concentration like this. So, if you take a p-type semiconductor, in this p-type semiconductor, the majority carriers are nothing but the holes. So, holes are the majority carriers like this. And of course, there may be a presence of minority carriers also. So, what are the minority carriers here? These are the minority carriers like this. These are the minority carriers, nothing but the electrons. And you know, for the formation of these holes, there should be some immobile ions which are meant for generating this. That means, if you take the semiconductor here, if you add the third group elements here, then only there is a chance of getting the more number of holes like this. So that's why it is nothing but a p-type semiconductor. In this p-type semiconductor, the immobile ions are nothing but, you can say, acceptor ions. Acceptor ions means negative ions like this. So these are the acceptor ions here. This is the acceptor ions. Similarly, for formation of this n-type semiconductor, in this n-type semiconductor, you have to add the fifth group elements like this, and the majority carriers are nothing but the electrons. Electrons are the majority carriers, and the minority carriers are nothing but your holes. So let me say, holes are nothing but the minority carriers. For getting the more number of majority carriers is like this, there should be some donor ions. So what are the donor ions? Donor ions means they are immobile ions like this. These are the immobile ions like this. So this is nothing but your n-type semiconductor. So this is p-type and this is n-type. And once you know this carriers inside the semiconductor, let me conclude like this. Let us take a semiconductor now. So if you take a semiconductor like this, and if you are taking the charge carriers inside, there may be electrons and as well as holes also. These are nothing but the holes. Holes will be there, and as well as ions also will be there. What are the ions you are having? You are having both positive ions like this, and one more thing is negative ions also you are expecting. Negative ions means these are the negative ions like this. These ions are immobile. So let me tell you, if you are taking the charge densities in a semiconductor here, these are the plus ions, these are the negative ions, that means donor ions and acceptor ions. Let us say the donor ions density is ND. Let us take that, okay? Let us take that the density of the donor atoms is nothing but Nd, and for the acceptor atoms is nothing but Na. The concentration of electrons is nothing but N. The concentration of holes is nothing but P. That means, if you take any semiconductor, there is a chance of having four types of carriers: electrons, holes, donor ions and acceptor ions. So these are the densities I am telling you. Now let us assume that the semiconductor is electrically neutral. What do you mean by this electrically neutral? Positive charge must be equal to negative charge. So what is the positive charge here? Positive charge means you can say this is positive and holes are also positive. That means Nd and P are nothing but the positive. So you can take that Nd plus P, density of donor ions plus hole concentration must be equal to. What is the negative charge inside the semiconductor? Acceptor ions plus electrons. That means you can say Na plus N. This is. So this is the basic equation required to tell about the electrical neutrality of the semiconductor. Here the positive charge must be equal to negative charge. Now let us take I am taking N-type material. So for N-type material, you can say Na must be equal to 0. That means acceptor ions is equal to 0. There is no question of acceptor ions for N-type material. That too, whenever you are adding this, whenever you are forming this N-type material, definitely you can say your electron concentration must be very, very greater than the hole concentration. That means you can say N is very, very greater than P like this. Apply this condition here. You can say Na is equal to 0 and electron concentration is very much high compared to this. Then you can say that Nd plus P is equal to N. This is the first equation. Applying this condition N is very, very greater than P, then P can be neglected. Then Nd is approximately equal to N. So what does it mean? The meaning is very simple, my dear friends. The electron field concentration must be approximately equal to the density of donor atoms. This is for which material? N-type material. And if you take a semiconductor, and generally I have taken a semiconductor, I have written this expression here, and finally I am telling for N-type material I can say N is approximately equal to Nd. Similarly, if you just assume that the material is P-type, then I can say P is approximately equal to Na. Now, using a single semiconductor, we are not having any practical applications. Generally, in future, what we are going to do? We are going to put P-type material and N-type material side by side. So, I would like to tell very clearly which material it is, which carrier it is. For that, what I mean to say is, I would like to use a notation for N-type and P-type like this. Now, let us recall our mass action law here. For N-type material, the mass action law you can write like this. Np is equal to Ni square. Just now I told you. The product of free electron and hole concentration must be equal to Ni square, square of the intrinsic concentration. But for N-type material, in order to say that it is an N-type material, I am using the notation like this. Nn plus Pn is equal to Ni square. Just observe here, this N is indicating that it is the type of the materials. Now, just now I told you, for N-type material, Nd is approximately equal to N. That means I can say Nd is approximately equal to Nn because it is for N-type material. So, I can write down here Pn is equal to Ni square divided by Nn. What is Nn? Nn is approximately equal to Nd. Therefore, Pn is equal to Ni square divided by Nd. This is the expression you have to use. Friends, just observe what is this expression is telling. This expression is telling very clearly holes in N-type. If you are taking an N-type material, for example, if you are taking an N-type material is like this, majority carriers are electrons and minority carriers are the holes here. But this expression is, for N-type material is calculating holes in N-type means minority concentration is equal to Ni square divided by Nd. This is the expression we are using. And remember, in the future classes also, our interest is not on the majority carriers, our interest is only on the minority carriers. You can ask me, what is the reason for this? Suppose, for example, if you take entire class, This entire class is listening to all the classes. They are getting an excellent knowledge. And 100 members are okay in this class out of 110. But I am interested for those 10 members also, because they are the minority carriers which are not concentrating on this. If I make a change for those 10 members, the class result will be excellent. That means, for example, if you are taking a class of 100 members, let us say that the class is of 100 members. And out of these 100 members, if I say 90 members are studying very well, and if you are making a change in this 90, there is no significant at all. So the remaining 10 members, if you make a change here, that means if you are taking care of only, suppose for example 5 persons, then how much percentage of increase? 50%. Out of 10 members, if I make a change in 5 members, that means out of 10, 5 members are changing into this environment, then 50% result will be enhanced here. So very simple, my dear friends, everywhere minority carriers are much more important to tackle. If you tackle the minority carriers, then definitely your result will be excellent. So Pn is equal to Ni square by Nd. What is this Pn? Holes in N type. That means minority carrier concentration must be equal to Ni square divided by Nd. So in future classes also you have to calculate the minority carrier concentration. Our interest is always to concentrate on the minority carriers, not on the majority carriers. Even suppose for example, I am telling you a small example. If you are taking an election in a constituency, and if you are sure that all these villages are doing a favor for your party, only one village is actually having a problem. So where you have to concentrate for getting the better result, you have to concentrate only on that particular village. If you are in a position to make a change in that village, you are going to get an excellent result, because already other villages are favor to you. Exactly, if you are taking the semiconductor, majority carriers are already doing excellent things. So the only thing is you have to change the minority concentration. That is the reason our interest is always to analyze the minority concentration. So the minority concentration means holes are minority in N-type semiconductor. Therefore, Pn is equal to Ni square by Nd, the most important equation for calculating the minority concentration here. Similarly, for P-type material, I can write like this. So for the same equation I am taking here, Nd plus P is equal to Na plus N. This is the basic equation in a semiconductor. Now I am considering for P-type material. So for P-type material, I can say Nd is equal to 0. That means density of donor atoms is equal to 0. Therefore, I can say P is equal to Na plus N. And whenever you are using the process of doping, in P-type material, the majority carriers are holes. That means P is very, very high compared to the electron concentration. So P is very, very greater than N. Therefore, I can say Na is approximately, P is approximately equal to Na. This is the basic thing you have to use in your mass action law. So for P-type material, what is the mass action law? Mass action law is nothing but Np into Pp is equal to Ni square. Therefore, I can write down here what is Pp. Pp is approximately equal to Na. Therefore, Np is equal to Ni square divided by Na. So, this is the equation for finding the minority concentration in P-type material. In P-type material, what are the minorities? Electrons in P-type. Electrons are the minority carriers. So, electrons in the P-type is equal to Ni square by Na. So, if you take this equation and that equation, Pn is equal to Ni square by Nd and Np is equal to Ni square by Na, these two equations are meant for calculating the minority concentrations in a semiconductors. So, finally, I would like to tell you, if you take a semiconductor, there is a chance of having 4 types of carriers here. One is nothing but electrons, holes, acceptor ions and donor ions. And as the semiconductor is electrically neutral, I have written positive charge must be equal to negative charge. Then I have applied all these equations for n-type material and p-type material using the mass action law. So, this is the way of actually calculating the minority concentration in semiconductors. Okay, I hope you understood this. And one more thing is here, minority carrier concentration is much more important compared to the majority concentration, because I have already given an example also. I hope you understood how to calculate the minority carriers concentration in semiconductors. Okay. So, now in the next class we are going to study what exactly this generation and recombination of charges in a semiconductor. Okay. Thank you.